Okay, video 2 is all about implied domain. So implied domain is what is the equation itself telling us, okay? So when we are looking at the equation itself, well, you could double check with a graph, but there are certain facts about an equation that you need to start recognizing. So first of all, where this discrepancy comes from, and the only time we have issues is when we have a square root or we have a fraction. The reason this is because this is where the errors come from and what certain values cannot go into an equation. So for implied domain, usually what you're asking yourself, is there anything x can't be? Okay, so in a square root, what can't you take a square root of? So if you were to put, say, 9 in your calculator, what is the square root of 9? Well, the square root of 9 can give you a positive 3 or a negative 3. What if you put into your calculator the square root of a negative 9? What number times itself gives you a negative 9? Well, never. Can't be nothing. Okay? Any number times itself will always be a positive number. Therefore, under a radical, can never be negative. You can have 0, but you can't have a negative. So inside whatever, if you have a radical of x, x has to be greater than or equal to 0. It can be 0, but it has to be bigger or equal to. Okay? And we'll look at what that means in a second for the equations that are up on top. The other type of problem that comes up is when you have a denominator. So I can have 1 divided by 1, and that's 1. I can have 1 divided by 2, that's 0.5 or a half. What happens when I do 1 divided by 0? This was our problem when you had slope, rise over run. If you didn't have a run, it was like you were in two places at once, which never made sense. This is what we called undefined. You can never have a 0 in the bottom in our denominator. So there are two ways to look at this. You can say x can't be equal to 0, or a lot of times with the interval notation, because this would be set notation, interval notation, you would say negative infinity to 0, and we use a parenthesis because you can't be 0, union, and then 0 to positive infinity with parentheses. Now, again, your book really works with interval notation, so you want to understand how to write interval notation. And these are how we're going to look. So in your notes, this is what I would want you to have. These are our two main examples that come out with restrictions on the domain. And that is where we called implied domain. So there's always a restriction on it when there is an implied domain. Otherwise, most of the time, and I would say 90% of the time that you look at a function, it is all real numbers, because there is very little functions out there where x has a restriction on it, like in these two examples. Okay, so let's look at A. A has x plus 3 as the equation. Okay, now we said a radical has to be greater than or equal to 0. So this is what we need to solve. Now you could solve your inequality just like that. Sometimes it's a lot easier to look at this like this and say, when is x plus 3 actually equal to 0? Well, if we were to solve for x, we have x is equal to negative 3. Okay, so to write my domain, I would say domain, if I was doing set builder notation, would be x such that x is greater than or equal to negative 3. And that's where that inequality comes back in. Okay, that is set builder notation. If this was a paper test in class, I would allow either one. As of right now, I can't go ahead and accept both because we're going to be online, so it's going to be based on what Pearson wants. Okay, so that is set builder notation. Interval notation would be the bracket. You have your -3, and that's going to go all the way up to positive infinity. Okay, now if you ever want to double check your work, always go and look at your graph. A graph like this would be at the +3. It would start right here and look like a little rainbow. And you could put that in Desmos and double check. Okay, I am going to move up the screen so we can write B down below. Okay, so now B. We have g of x is equal to the square root of x over x minus 5. All right, so here we have a combination. The square root of x is telling me I have to be greater than or equal to 0 because I can't be negative. And the bottom is telling me x minus 5 cannot equal 0. So you want to solve, in this case, both of them. This is an example where looking at your actual graph might be a lot easier than looking at the equation. But we're going to solve this together. So for this one, x has to be greater than or equal to 0. If I was to solve this, x cannot equal 5. Well, 5 is bigger than 0. So this is where our union is going to come in. We're going to start at 0. But instead of going all the way up into infinity, I have to go up until 5. Parenthesis, because I can't be 5. Union, parenthesis, 5. Now I can go up to infinity. So this says my domain starts at 0, goes all the way to infinity, but has a hole at 5. Okay, next class we're going to do a lot more practice, but this would be, again, your implied domain. And that's how you would write your equation. You could also look at your graph to double check what this looks like. Okay, on the last one, you have C is the square root of 3 over 4s squared. Now, if you realize that's a quadratic, there is nothing s can't be, right? So there is no obvious restriction. But let's think about this problem again, which is why it's called implied. What is implied with this problem? It's the area of an equilateral triangle. What numbers don't make sense for an area? Okay, so negatives are never going to happen. Area cannot be negative. So area has to be greater than or equal to 0. You can have no area, but you can't have a negative area. Okay, so therefore here, this case, S would have to be greater than or equal to 0 because negatives don't make sense. If I was doing interval notation, that would be the bracket for 0, and it goes all the way up to positive infinity. I believe on the next page I have a little draw it for you to try your domain and range of some more extra equations.